Thank you all. So, regarding the presence of water ice on the moon, we have plenty of evidences nowadays. And this fact was also very well highlighted during the very first day of this conference here, but also during the first presentation given today. So starting from this fact, we are now interested in the detection of water ice on the moon for future missions, of course, and in situ resource utilization. So here we are trying to address several questions, like, is it water ice present at some depth? And of course, how much water ice it is present? Then, in what form we can find water ice? Is it maybe mixed within the regolith? Or maybe we can find it in the form of layers, massive layers buried within the dry regolith. And of course, the most important question here is, can the ground penetrating radar technique may detect water ice on the moon in different forms? So very briefly, the GPR is an instrument that has a transmitting and receiving antenna. And while moving on top of the surface, it sends small electromagnetic pulses that travel through the subsurface. And when the pulse encounter a very strong contrast in terms of permittivity of the material buried at depth, the wave is reflected back and received by the receiving antenna. So the very final product of GPR surveys are the so-called radargram, as the one shown here. And what we are looking for into a radargram is basically anomalies. And in this case here is reported this very bright anomaly, this very bright hyperbola, which is produced by a target buried at depth, which means that the permittivity of the target present very different value of permittivity respect to the surrounding environment. So we have to very keep in mind for subsequent discussion that strong electromagnetic contrast are produced by very strong contrast in permittivity. And so related to the water ice detection on the moon, here I report the permittivity values of material involved in water ice detection. And as you can see here, the permittivity of water ice, lunar regolith, and simulant as well, and regolith ice mixtures present very similar values of permittivity. And this fact is also very well highlighted when I add to this plot the permittivity of liquid water, which is around 80 on the vertical scale. So now, if we compare the Earth and Moon environment, we clearly see a very big difference. And so the presence of liquid water on Earth in the subsurface enhances the electromagnetic contrast, make it easier to detect target buried at depth. While on the moon, since we have a very dry environment, the electromagnetic contrast might be even lower. So in case we want to apply the GPR methodology on the moon, we have to take this fact into account. So in this work, we are trying to address two different scenarios about the form of water ice we can find buried within the dry regolith. The first scenario is, of course, water ice lenses or water ice layers, so a massive layer of pure water ice buried within the dry regolith. And in the second case, we have regolith ice mixtures, which is basically regolith completely saturated with liquid water, then frozen, and this frozen layer is buried within the regolith. So for doing so, we conducted several experimental activities in our facility using the so-called electric box shown here on the left. So the box was filled with a material that we can consider a very good simulant, regolith simulant in terms of permittivity values and the electric properties. And we use the so-called glass beads. So on the right, you can see a picture of the box. We use this plastic grid as a reference to collect the GPR lines. And we collected GPR data in two different ways. So we first put the target at the center of this grid below within the glass beads, and we collect the grid when the target is still frozen. Then we let the target melt, and we track the melting process, putting the GPR on top of the grid and let the GPR acquire data, one trace every 5 minutes for about 5 to 24 hours to track and follow the melting process. So when we knew that the target is partially or totally melted, we then reacquire the GPR lines following the grid. So very briefly, that's how we recreated the target. In the first scenario, we use frozen distilled water into a plastic bag. And in the second case, we use frozen saturated glass beads. So here are the results. So first of all, I want to show you the background acquisition when inside the target, the box, there is no target at all. And here, where is the black line, is a reference for the reflection given by the bottom of the box. So knowing that the depth of the box is 30 centimeters, we know that if we are looking into our radargram for an anomaly given by the target, it should be found between 20 to 30 centimeter depth. So now, what happened when we insert the first target, the frozen water ice layer? We insert the water ice in our box, and of course here we don't clearly see any kind of anomaly into the radargram. So in this scenario, the frozen target is not detected in this condition, in the laboratory condition. And as I mentioned before, we let the target melt and we acquire the traces every 5 minutes to track the melting process. And here, in this figure, what is the red arrow, is reported the very first trace acquired when the target is still frozen. And the red arrow indicates the position of the target into the box. And here, the amplitude of the signal doesn't indicate the presence of any anomaly, any target that has different permittivity values into the box. In fact, the amplitude of the signal is very similar to the background noise. But what happened when we let the target melts? Of course, the amplitude of the signal is enhanced by the presence of liquid water. And this fact is also very well highlighted when we required the GPR lines when the target is partially or totally melted. And here is reported the radargram when into the target liquid water is present, and it's clearly visible inside our radargram with this very bright hyperbola. So in this case, the target is detectable with the GPR only when liquid water is present inside. So now we are addressing the second scenario, the regolith mixtures, or also called icy soil. In this case, when the target is still frozen, we are able to detect it with the GPR. And in fact, into the radargram is clearly visible on the right side, this anomaly, the hyperbola produced by the target itself. And the difference between this scenario with the previous one is just related to the permittivity contrast, which in this case, the permittivity contrast is higher compared to the previous one, which allows the detectability of the target itself. And the detectability of the target in this case is even more highlighted when we let the target melts. And of course, the presence of liquid water enhances the reflection, giving this very, very bright hyperbola. So how we can conclude this work? Of course, the detectability of water ice on the moon depends on local conditions. And these are very preliminary results, but based on our results, we can say that if the conditions on the moon of the regolith led the permittivity values of the environment to be too similar to the permittivity of pure water ice, the detectability of water ice in this scenario, the probability is too low. But in the other scenario, when the water ice fills completely the pores within the grains of regolith and completely saturates the soil, in this case, the probability should be higher. But of course, the detectability of water ice on the moon is a very hot topic nowadays due to the in-situ resource utilization for future missions. So it is important to keep studying this topic, and of course, it requires systematic studies. So that's all, and I want to thank you all for your attention.